So this integral, one way of doing this integral is with a change of variable. If you change the variable, make the substitution y equals root x, then you'll get rid of the root x, and that might be an easier way of doing it. But I've chosen this one just to illustrate what happens if you have a branch cut and you have an even function multiplying that branch cut function. So you've got an even function and you're multiplying that by a function with a branch cut. So in this case you can get away with, so obviously root x has a branch point at 0, we're integrating from 0 to infinity, so we choose to make the branch cut along the real axis. But you can then get away with, as we'll see, a semicircular contour rather than a full circle. Basically also because this doesn't have any singularities on the real axis. So our contour looks like this. Its radius r, and as always this is distance epsilon. It's our contour gamma, and we consider the contour integral around gamma of this. So as epsilon goes to 0, as r goes to infinity, this bit along here is the integral we want, I. Then we need to just check that this integral around here goes to 0, so the limit as r goes to infinity of the integral from 0 to pi of, now dz turns into r times e to the I theta, I times d theta, and we've got r times e to the I theta square rooted on the bottom, and a squared plus r2 e to the 2I theta. Okay, so overall we've got r squared on the bottom and root r. So this goes off like order r to the 3/2, so that's no problem, that goes to 0. Then this bit coming back, so again along here we've got z equals r times e to the I pi. So integrating from 0 to infinity, this gives me dz equals minus dr as before, so I'll put a minus sign here, and I've got dr, and here I've got root of z, so this is sort of why I've written it as root r times e to the I pi. I know exactly what to do with this. If I've written minus 1, I might think, oh well, should it be square root of minus 1 should be plus I or minus I. This tells me it has to be e to the I pi by 2, which of course is I. So I have plus I here, and it's root r. When I substitute this into here, and the rest just is a squared plus r squared. Then the last bit I need is this bit around here. So it's the limit as epsilon goes to 0 from theta equals pi to pi by 2. And I've got the same thing as before, but with epsilon. So this gives me root epsilon e to the I theta, and a squared plus epsilon squared e to the 2I theta. Okay, so as epsilon goes to 0, we've got no problem with this. We just end up with epsilon divided by root epsilon, which gives us something which is of order epsilon to the half, which does indeed go to 0 as epsilon goes to 0. So what are we left with? So we've got 1. Now again, this is minus, and we use the minus to flip the sign. So we've got basically 1 over I times the integral we want. So 1 over I is the same as minus I. So this is going to be equal to, okay, we need the residue, the pole. So there's a pole at z equals IA. So this thing here is then equal to 2 pi I times the residue. Yeah, so I'll tidy up things again. Of so that's 2 pi I times, okay, so this is P, this is Q, so I've got 2z times root z. Okay, so this I can write as a times e to the I pi by 2. So when I square root that, I've got root a times e to the I pi by 4, and that's multiplying 2z, which is 2ia. Okay. So cancelling some things out, I can cancel the 2 i's, and that gives me pi over sorry, I shouldn't have this 2 here still. The 2 came from here. Okay, so it's a to the 3 halves from these two. The 2i cancel with this 2i. I got the pi, and I've just got e to the I pi by 4, which I can also write as, well, it's just a matter of what the best simplification is. E to the I pi by 4 on the bottom is the same as e to the minus I pi by 4 on the top. That's actually quite a useful thing to have, because that in fact is the same as 1 minus I over root 2. So this then cancels this 1 minus I here, and we get the final answer I is equal to pi over root 2 times a to the 3 halves.